mic and see them.
Alright, so we are the Biodiesel conversion system. I know we're the second to last group, so just hang in there, guys. I'm Addie.
I'm Ronnie. I'm Lydia.
I'm me.
Alright, so our problem statement is to design a biodiesel conversion system for California State University of Sacramento to convert waste vegetable oil into usable diesel fuel. And this is the design at the end of last semester. It starts with the waste cooking oil going through the filtration unit, and then it gets pumped into the processor tank where it's heated and circulated and the chemicals are added, and then the reaction occurs. And then it goes to the dry wash tank where impurities are removed to ensure good quality biodiesel, and then it goes into the storage tank.
So this is our current design for 191. This is the way it actually sits in our room. You're going to notice that there's a couple of changes from our previous design that will actually go into detail in the next couple of slides. So the first big change was the serviceability of our components. We never even took this into consideration in 190, so we came into the 191 and just started, trying to put things together, and we realized there was no possible way we could put it together. Plus, we would never have access to any of our components if they were to mess up or we needed to service them or anything. So the solution to this was to add unions to most of the ends of our components, major components, and that made it easy to service them, to take them apart, move things around. So that was definitely a big change that we took into consideration.
All right, since we had to add all these additional pipings and everything for serviceability, it also changed the height dimension of our entire system with different components. Our reaction tank stand, actually, we had to weld on an additional extension onto it because after we added it, the stand was too short for it. And then also our methanol tank, we also had to extend. And then another part of the system was our pumps. We shouldn't have them sitting on the ground because if something were to spill on it, it's definitely not good for the pump. So we went ahead and made stands for all of our pumps. In our new design, we were also able to eliminate a lot of piping. There was just a lot of unnecessary pipes. So to save money and then also complexity, first of all, by using a T, we were able to eliminate a whole length of pipe from the reactor tank into the dry wash system. And it was basically just using a simple T and 2 valves, and so that was one big design change. And then also from the filtration tower into the reactor tank, we originally had a piece of stainless steel pipe there, but just we ended up using a clear plastic hose because it was easier to work with, cheaper, and then also it's pretty cool. You can see the filtered oil go through, and then yeah, also cheaper and okay. So another thing was the glycerin removal. Originally, the reactor tank was high enough in the room to where we could just drain it off the bottom. But then after addressing the serviceability issue, we had to raise everything, and then there was not enough room. So we had to relocate the removal system, and basically this led to adding a pump. That way we could ensure that all the glycerin is removed fairly easily.
So now we move into the manufacturing portion of our project. Here's a list of the different manufacturing processes that we use. So first is welding, cutting, grinding, piping, polishing, and drilling. We're going to go into detail on these. So the first on the list was welding. So we kind of went into the machine shop trying to make our stands, the extensions, and all whatnot. And we went in there thinking, well, Mike makes it look pretty easy, so I think we can do it too. Well, little did we know, welding is not very easy. It's something that takes skill and practice. So it's definitely something that we should have learned, or that we should have tried to practice before going in there and trying to make stands, like right after the bat. So definitely that was some of the biggest thing we learned from the welding process.
All right, and then manufacturing our pipes. We thought we were originally just going to go in there, no big deal, out, read them out, no, super easy. Little did we know that it's much more difficult to machine stainless steel than regular mild steel. My comedian basically laughed at us and was just like, you really thought you were going to go in here and cut these pipes? So we ended up just outsourcing it to a different machine shop, and they were able to do it for us, get it to the exact lengths that we want. And then we simply connected all our pipe fittings pretty easily after that. But we learned a lot from this just because it put us behind in about 2 weeks because, we weren't able to cut the pipes right away.
Another thing we did was we painted all of the metal surfaces, that way to protect from corrosion, and we also polished the piping, and we did this for aesthetics because not only did we want our system functionally sound, we want it aesthetically appealing as well. One thing we learned though was it's probably best to do final painting and polishing after the whole thing's assembled, because we ended up moving things around so much and banging it up that we got a lot of, chips and scratches, but lesson learned for next time.
Alright, so one of our longest and hardest, most complicated problem was leaks. After the mid-semester presentation, we seriously thought that we were going to have our entire system fixed, up and running in no time, and we can be able to begin testing. We went to Home Depot, asked them what their best sealant was. They recommended Teflon tape. So sweet, we got the Teflon taped all of our fittings and pipes, tightened everything together, took a step back, looked at our system, high-fived each other. We're just like, wow, we're going to begin testing. We're actually going to pull this off and have a lot of time for testing. We filled it up with water, and it was ridiculous. There was leaks everywhere. Every single union, pipe fitting, joint, elbow, anything you think of, it sprayed water everywhere. Like literally sprayed water everywhere.
Okay, so we thought it's not that bad, we figured it really wasn't that bad, we could just tighten the pipes more. It was our first time using pipe wrenches and Teflon tape, so we figured we would just re-Teflon, re-tighten, and we did that multiple times, and then we got it all tight. We high-fived, thinking, it's going to work this time. We filled it with water, opened the valves, and this time, instead of spraying, it was just a little drip, which was so frustrating because we were this close, but still just not there yet.
So feeling so frustrated, we're about to give up. We've been doing this for weeks on end, we're about to give up. So we were like, you know what? One last time we're going to go to Home Depot. So we go, and who do we see there? John Oakley. And he's just like, yeah, I'm going there too. So he brings up, he's like, here's this pipe coop. I was like, pipe coop, what is this? We're like, okay, you know what? We'll give it a try. Might as well. We have a bunch of leaks, so let's just do it. So we go. At this point, we've taken the system apart millions of times, or at least it feels like it. So we regoop it. We, start tightening up with our pipe wrenches. We're pretty much pro plumbers now. Pipe wrenches are an extension of our body now. Seriously, I feel so comfortable with the pipe wrench now. So we regoop everything. We tighten it, and we're like, you know what? We're not gonna high five this time. We're just gonna not jump the gun. Let's wait. Let's test this out. We open up a valve. No leaks. We're like, yes, we finally high five. We're just so happy. So we just want to reiterate how ridiculous leaks are. From hearing every other group, it's we weren't the only ones with the trouble. We definitely now feel like pro plumbers. Plus, we understand why plumbers charge so much. It's ridiculous.
All right, so safety. We'd like to thank God for Mike Christensen for bringing in the safety inspectors to take a look at our system before running any biodiesel, because it can get pretty dangerous. It turns out that the room is actually too small for our system, and we don't meet any of the fire standard codes. There has to be a certain amount of distance away from the wall to your actual system to ensure that if anything does happen to someone operating, they have an ample amount of time to get out and exit the building, which we do not have because the room is too small. Also ventilation issues and such. And then also some of the drains, we don't want to spill any of the dangerous chemicals down the drain and contaminate any of the wastewater. So with all the potential hazards involved, we all got together and determined to relocate our system outside. So we'll be doing that during the summer, relocating it and moving it all outside. And the current room will be used for quality testing purposes. And we actually started testing the system with water because it's a lot safer. And then we knew that there was no leaks to fix it. And that way we knew once we ran the entire system with water as if we were running it with oil to ensure that our system was mechanically sound and worked exactly the way we wanted it to.
So, since we couldn't actually make biodiesel in our system, and we were testing it with water, we decided to make some smaller test batches of biodiesel. That way we could just test and make sure that we are getting a successful reaction and that we could do quality testing. And just to really understand the process of biodiesel. So we made multiple batches, and what we did was, once we got to the settling process and the glycerin settled, the biodiesel is on the top, and we used the clarity test, which is also known as the 27-3 test. So what you do is you take 27 milliliters of methanol and you mix in 3 milliliters of biodiesel, and then you shake it for 30 seconds and you let it sit for 5 minutes. And then at the end, if you get a homogeneous mixture, you know the reaction completed successfully. And so the first couple batches, it was not homogeneous. You could see sediment on the bottom, and so we knew the reaction did not occur. But soon enough, we did get successful batches, and those pictures right there are of the clarity test. We did successfully make some biodiesel.
So, since we couldn't do anything with oil, we ended up doing everything with water, like was mentioned. So, we had to test our filtration housing. So, first we had to test our heater to make sure we got accurate numbers. So, first we did all the theoretical calculations, and we assumed that our Q dot was constant, and then from there we found the time it would take for the water to heat up to 105 degrees Fahrenheit. And then from there, we did our experimental results and found that it would take 2.5 hours, which was about the same as our theoretical calculations. So from there, we wanted to kind of go back and relate it to the oil. And then, so like that, we found the ratio between the specific heat of oil times its density divided by the specific heat of water times its density, and then multiplied that times the time, and that would give us the time approximately it would take to heat up the oil, which was about an hour.
All right, and for the reaction process, we had to calibrate the heater to make sure we set it at a proper setting to ensure that it maintained a temperature of 130 degrees Fahrenheit throughout the entire reaction. So basically, we just ran some water through it and did some trial and error to try to get the knob right, and then waited until the water reached a steady state of 130 degrees. We finally found the proper setting and adjusted it accordingly. We used the same equations from earlier for the filtering heating process, and the theoretical value that we came up with to heat water at 130 degrees Fahrenheit, it takes about 2.86 hours, and our experimental value after timing it was about 3 hours. And we figured that this was very reasonable since, there was some heat loss in the system, the lid wasn't on all the way, and then we didn't put in any of the insulation since we're going to have to take it apart anyways to put it outside. So it seems really reasonable.
So as also part of the system, we were going to automate the system. So some of the components we have used in the automation is obviously a PLC. The PLC is communicating through a relay, activating the relays, and actually making our output devices, which are the solenoid valves and the pumps, actually work. Get them running and turning on and turning off whenever we need them in our system. So here you can see that down there is a basic circuit for a relay. Relay, probably already know, it's just an electromagnetic coil in there. Once you activate the coil, the normally open switch closes, creates a circuit, and then this relay also provides the power that's needed to run our pumps, which are on the left-hand side, and the valves that are on the left-hand side, and the pumps that are on the right-hand side. In the middle, you'll see a circuit breaker. We put the circuit breaker in there so that ever we have a wire voltage go up and down, that circuit breaker will protect all our valves and our pumps. So
we would like.
Oh, there's one slide. Okay, so we're missing one slide. The programming that was done for the PLC was done using ladder logic. Ladder logic, actually, when you open the program, it looks like a ladder. It has the runs. The language is read when the PLC reads the code. It reads from left to right. Everything on the left-hand side is your inputs, and on the right-hand side is your outputs. And it's actually a very interesting program. It has a lot of coils and internal coils, and it uses internal coils from the PLC itself and the internal memory of the PLC. And that's how we designed our coding to run these pumps and valves.
So we would like to give a special thanks to Mike Christensen. Thank you so much for sponsoring our project. We really appreciate the constant communication throughout the whole year. You're very prompt with getting back to emails, phone calls, any concerns we have. And also just the fact that you never once doubted our engineering abilities just really gave us that confidence we needed to feel like we could complete this project. And just always checking in and genuinely caring about the project. And we really appreciate it. Thank you, Mike.
We'd also like to thank our professor, Patrick Holman. Thank you so much for always going above and beyond. Like, all of the days he actually did come in afterward, it was around like 4:30. He came in, rolled up his sleeves, grabbed a pipe wrench, and started plumbing with us. He felt the frustration also with all the leaks, which we were really thankful for, like, all his support. It just, the fact that he cared so much, he just kept checking in on us, trying to get us to finish the project. Thank you so much for all your support and help for everything.
So, third, we would like to thank Mike Newman, who isn't here, but I'm definitely going to just keep on going with it. We're just thankful that he loaned us pipe wrenches. Pretty much every pipe wrench that they had in the machine shop, we had for over 5 weeks. So, sorry if anybody else needed them, but we sent you behind. We also just wanted to thank him for the manufacturing advice. We would go into, show him our design. He's like, no. This is way too complicated. You can't even make that. Let's do it this, and this. So that was way better. And we also just, with tough love, Mike came into our room and was just straightforward. He's like, you guys, this is ridiculous. You guys are probably not going to graduate. Or he would come in, he'd come in and we'd have leaks spraying and he would just laugh in our face. So, that really motivated us to just work, and was like, no, Mike's not going to laugh at us next time. And it just really made us work. And we're just so grateful for all of that, all the tough love.
And last but not least, it's Rustin Wolf. Thank you for being our advisor, and thank you for all the pressure and the tough love. We look forward to every Monday we have this semester and last semester too.
All right, thank you. Questions, comments, concerns?
I was just wondering, you said it hadn't been tested really yet. When do you think it would be operational?
Oil?
And actually be able to use here on campus?
As soon as it's moved outside. We have to lay out some concrete and everything out there to make sure that we can anchor it before. We don't have an estimated time of when it'll be completed, but we're still committed to the project. Definitely this summer.
What about the summer heat? You guys put that, is that going to affect your system at all? When the sun heats down, or is it just be covered?
Well, the heater that we actually have a covered patio where we're setting it up. Plus, all of our heating elements have a thermostat built into it, so you actually set the temperature and it'll turn off when it reaches that temperature. So we don't really have to worry about changing that.
Probably better for the oil too, that it's hotter and easier to work with.
How many, did you guys verify that the equipment on campus can actually handle biodiesel? There's a lot of diesel vehicles cannot use biodiesel.
Yeah, a lot of vehicles cannot use pure V100 biodiesel straight into the vehicles. You have to make some components. Haven't spec'd it out yet exactly which vehicles we have on campus. We're going to work on that also during the summer.
Okay, thank you.
That's great.